Okay, let's review acid-base neutralization, reacting stoichiometric quantities of acid and base. So this question asks us to react potassium hydroxide with nitric acid. And first we want to be able to write both a neutralization reaction, the overall equation, and then a net ionic equation as well. So potassium hydroxide, really important that we remember that that's a strong base, and nitric acid is a strong acid, which allows us to know that they are completely dissociated, as of course is the very soluble potassium nitrate, which allows us to know that the net ionic equation would cross out our spectator ions, resulting in OH minus from the strong base, H plus from the strong acid, producing water. And if we want to calculate the quantity of what volume of base would be required to neutralize 25 mils of nitric acid, let's take a look at that. First, let's look at maybe we want to say it's the long method. Let's remind ourselves that molarity is moles per liter or millimole per milliliter. So if we cross multiply molarity times volume of the molarity of the acid times the volume of the acid would give us millimole of acid. And this is a monoprotic acid, 1 H plus per acid molecule. And then of course the reaction, we notice, is a 1-to-1, 1 hydroxide reacting with every 1 acid ion. And so, of course, these don't make any difference mathematically, but the moles of acid then will be neutralized by the same millimole of hydroxide ion. And then we can plug that back into our formula. Knowing the millimoles of hydroxide, we can solve for the volume if we know the molarity. And lo and behold, 37 will pop up. But let's look at a little bit shorter way to do that. We want to be able to use what I would call the neutralization equation, which we've called the dilution equation in the past. The molarity of the acid times the volume of the acid, which is of course moles or millimoles, and upon neutralization that will be equal to the molarity of the base times the volume of the base, or the moles of the base. And so all the same math is down here, leaving out the 1-to-1 ratios, and so we can simply solve for the volume of the base as 37 mils. Now we can do the same. Let's calculate what volume of potassium hydroxide we'd need to neutralize some nitrous acid. And we don't know much about Ka yet, and we actually don't need it. We don't want to be distracted. We should write reactions, pause, and try that. And so there's a difference here. We've got our potassium hydroxide, our nitrous acid. Of course, we're generating water, and we've got the very soluble potassium nitrite. However, we need to remember that our nitrous acid is a weak acid. It's not one of our 7 strongs, so by default, or the presence of this Ka, which we don't know much about yet, but would tell us that this is a weak acid. So we can certainly know that the potassium hydroxide is ionized, the alkali nitrite is ionized, which allows us to cross the potassium out of our net ionic equation. But we can't eliminate this nitrite because as a reactant, the nitrite is very much stuck. Most of it, 95% of it, is stuck as a molecule. So we want to represent the nitrous acid as a molecule. So that needs to stay in the net ionic equation. The punchline here is, though, solving for the quantity of base required will be the same procedure, whether or not strong acid or strong base, because all of the H's, even though a lot of them are very much stuck, they will be ripped off by the very aggressive incoming strong base. So even though these are stuck to the molecule, the strong base will grab them, produce water, leaving the nitrite ion alone. So let's look at the quantities. And we can look at the long version down below. Molarity times volume will give us moles of acid, all 1-to-1 ratios, and then plug back in. Or we can simply use our dilution equation. Molarity times volume gives moles of acid, and we can set that equal to our moles of base, solving for the volume of base required. And we don't want to be distracted by the fact that this is a weak acid. The same amount, weak or strong, of hydroxide will need to react with the H+, whether they are attached in this weak acid or if this were NO3 and they were separated as in a strong acid. Now we could take a look at acetic acid, HC2H3O2, obviously also a weak acid, but doesn't really matter when we're thinking about neutralizing it with barium hydroxide. But there's a twist here, because we should remember that barium is a 2+ ion, so there needs to be 2 hydroxides, and that's going to change the stoichiometry of the equation. So let's write the overall neutralization, not forgetting that this is a strong base, this being a weak acid. So because of this 2, buy 1, get 2 base, if you will, we need double the acid to attack the base, or the base twice as much, or half the amount of base can attack twice as much acid. In our net ionic equation, because this is a weak acid, yet this is a strong base, we can, and this of course an acetate, barium acetate, will be soluble. We can cross the bariums off of our net ionic equation, but we cannot cross off the acetates. Now there's a little bit of a trick here. We have to watch out because of the stoichiometry, and it's a little disconcerting. Notice that this 2 is on the base side, and you might be distracted and think you should put it on the acid side. But that's because molarity times volume will give us moles of base, but the actual base molecule, but it gives us twice as many hydroxides, so we need the 2 on the base side. Or we could look at the extended version, where we would take our molarity times volume to get millimoles of base, and here's our 2-to-1 ratio, 2 hydroxides for 1 base. Again, the acid reacts with the hydroxide in a 1-to-1 ratio, ultimately giving us twice as much acid required to go with this original amount of base, because there's 2 bases, 2 hydroxides for every base, and then we can plug that back in and end up with the volume. We can, of course, use the short version, but we have to watch out for where we place this 2 ultimately to end up with 210 mils. So giddy up, get practicing with the pH loop and neutralization worksheet to make sure that you're ready to go and to move on to the next part of acids and bases.